All right, today we're going to dive into something that is truly one of the marvels of the modern world. We're talking about how we turn one of the most common things on Earth into, without a doubt, the most complex object humanity has ever mass-produced. This, my friends, is the alchemy of the digital age. Believe it or not, the incredible journey of every single AI chip starts right here, with silicon dioxide. You know it better as just sand. And this is where that journey ends up. It's like an electric metropolis with billions, literally billions of components, forming the thinking heart of a supercomputer. A single circuit built one painstaking layer at a time. So that's the billion-dollar question, isn't it? How in the world do you get from a humble grain of sand to the hyper-advanced brain of an AI? Well, it's a months-long odyssey of physics, chemistry, and mind-bending engineering. And it all happens in some of the cleanest rooms on the entire planet. And look, that's not just hyperbole. The scale of this process is absolutely monumental. A single stray speck of dust, something smaller than a virus, can completely destroy a chip that's worth thousands of dollars. The level of precision needed is, well, it's almost impossible to wrap your head around. Okay, so let's break this incredible transformation down into 4 major stages. First, we'll look at forging the perfect silicon canvas. Then, printing circuits with what is essentially impossible light. After that, we'll see how atomic-level switches are carved. And finally, how the whole thing gets wired together. You know, you can't build a skyscraper on a shaky foundation, right? Well, same idea here. Everything, and I mean everything, starts with creating a flawless, perfectly circular disk of pure silicon. We call it a wafer. And getting this first step right is absolutely critical. This number you're looking at is the level of purity we need for semiconductor-grade silicon. It's called 9 nines pure. What does that mean? It means for every billion silicon atoms, you're only allowed to have one single impurity atom. It's a standard of perfection that's just mind-boggling. To put that in perspective, try to imagine a line of sand grains stretching all the way from Los Angeles to New York City. Now, imagine having to find and remove a single discolored grain from that entire line. That's the level of purity we're talking about. So, why all the fuss? Because at this tiny scale, any impurity acts like a fatal pothole for electrons, wrecking the flow of electricity and making a billion-dollar chip completely useless. So how do they achieve this perfection? Well, funny enough, it's with a technique that's over 100 years old. You take purified silicon, melt it down in a special crucible, and then you dip this tiny, perfect seed crystal into the molten goo. Then you slowly, very slowly pull it out. As it rises, the molten silicon cools around it, perfectly copying the seed's atomic structure, growing this massive single crystal ingot that can weigh hundreds of pounds. Okay, so we've got our perfect silicone canvas. Now comes the really wild part, photolithography. This is the heart of the whole process. Think of it like photography, but instead of pictures, you're using light to print these incredibly intricate circuit designs onto the wafer, layer after microscopic layer. Now, to keep making chips smaller and faster, to keep Moore's Law going, the industry hit a wall, a physics wall. They needed to use light with a much shorter wavelength. But this light, extreme ultraviolet or EUV, is a real diva. It gets absorbed by practically everything, including air and even glass. So you can't use lenses. The solution? A whole new system that operates in a perfect vacuum and uses a series of ridiculously complex mirrors instead. And how do you even make this impossible light? Well, it's basically an active controlled violence. Inside the machine, a super powerful laser blasts a microscopic droplet of tin, 50,000 times every single second. Each zap vaporizes the tin into a super hot plasma, which then emits that exact 13.5 nanometer light you need to print the world's most advanced chips. It's just insane. You know, the challenge of mastering EUV light was so incredibly difficult that every other company trying to do it just gave up. And this success didn't just create a business monopoly, it created a physical choke point in the global supply chain. This one machine became one of the most powerful strategic assets on the entire planet. So we've printed these beautiful patterns, but how do they actually become functional? Well, the next steps are etching, where we carve those patterns into the silicon, and something called doping, where we transform the silicon itself into a material that can actually compute. Doping is really the atomic level alchemy we were talking about. Pure silicon is actually not a great conductor of electricity,
But if you sprinkle in just the right amount of specific impurities, you can completely change its electrical properties. You add something like arsenic, you get N-type silicon, which has extra electrons. You add boron, you get P-type, which has holes where electrons should be.
And when you create a little sandwich of these different doped regions, you get a transistor. By applying a tiny bit of voltage to that middle P-type layer, the base, it acts like a gatekeeper, controlling a huge flow of electricity from the source to the drain. It's a tiny, lightning-fast on-off switch. Now just do that a few billion times, and you've got a processor.
So, how do you get these special atoms into the silicon with such pinpoint accuracy? You can't just sprinkle them on. One of the main ways is a process called ion implantation. You basically ionize the impurity atoms, and then you literally shoot them, like microscopic cannonballs, into the wafer at incredible speeds. Okay, at this point, we have billions of tiny, isolated transistors. They're amazing, but they're completely useless until they're connected to each other. The final major stage is building that multi-layered, microscopic nervous system of wiring that brings the whole chip to life. For a long time, this wiring was made of aluminum. But as chips got faster, aluminum was becoming a huge bottleneck, like a tiny clogged highway. Then, in the late 90s, IBM had a massive breakthrough. They figured out how to use copper, which has about 40% less resistance. That one change immediately made chips roughly 15% faster and way more power efficient.
But there was a huge problem. Copper is like kryptonite to silicon. It leaks in and poisons it. So they had to invent a totally new, really ingenious technique. Instead of putting metal down and etching it away, you first carve trenches into an insulating layer. Then you line those trenches with a protective barrier, fill the whole thing up with copper, and then polish the surface perfectly flat. What you're left with are perfect copper wires embedded safely in the insulator.
And here's the crucial thing to remember. A chip's speed isn't just about how fast the transistors can switch. It's more and more limited by the traffic jams in the wiring that connects them. If that nervous system is slow, it cripples the entire chip, no matter how fast the individual brain cells are. And the scale of this nervous system is just astounding. If you could take all the microscopic copper wires on a single advanced chip and unravel them, lay them end to end, how long do you think that line would be? A few meters? Maybe a football field? No. The total length would stretch for several kilometers. Which brings us right back to the beginning. We started with a simple grain of sand, and through this incredible process, we turned it into billions of atomic switches, connected by kilometers of copper wiring, all built with unimaginable precision, on a tiny sliver of silicon no bigger than your fingernail. This whole microscopic journey, from sand to a thinking machine, has literally created our modern world. And that leaves us with a really big, really important question to think about. What are the implications when our entire digital civilization rests on a manufacturing process that is this impossibly complex, this geographically concentrated, and ultimately this profoundly fragile?